Hi everybody, welcome to Lecture 2 of Digital VLSI Design. This lecture is all about the Verilog Hardware Description Language, which is the example of a hardware description language that we'll be using in this course. But most of the concepts are correct for VHDL or for System Verilog or other hardware description languages. So let's start with the important question of what is a hardware description language? And my straightforward answer is that a hardware description language, or an HDL, is not just any other programming language. In fact, we're usually used to programming languages that are sequential, they're serial. Commands come one after the other. In hardware description languages, what we're doing is we're not describing the flow of data that goes through a processor that works in sequence. Rather, we're describing actual hardware constructs that are all scattered around our chip, and they are all executing in parallel. That's a very hard concept to overcome, and it takes a while to understand it and get used to it, that things actually happen at the same time. It also means that code ordering is flexible. What do I mean by code order being flexible? Well, let's look at the example over here. In this example, we can write a equals 1, b equals 2, and then after it we'd write c equals a plus b. In a regular language, we would have a equals 1 happen first, then b equals 2, and of course c means 1 plus 2. And then c equals 3. The same thing happens in Verilog, but the interesting thing is that we can put this c equals a plus b first, then write a equals 1, and then write b equals 2, and we'll see exactly how to do that in the rest of the lecture. But in this case, c also equals 3, because a equals 1 and b equals 2 are happening in parallel to c equals a plus b. We'll try to understand that later on better. Okay, execution of codes is triggered by what we call events. So every time something happens, something changes, an event is struck, and then the simulator, which actually goes and tries to show us if our code is behaving like we planned for it to, will go and we'll figure out what happened exactly at that event. There are other types of simulators, but most of them are event driven simulators, and they are triggered by events. Okay. Since an event causes things to happen, it sees what changed, and it goes to what we call a sensitivity list, which is a list of signals that affect a certain construct we have there. So the sensitivity list looks and sees if one of the signals that are in the sensitivity list had changed, and that's when we know that a certain code section or construct is supposed to be executed. And it's very important to note that some things, because they're happening in parallel, are unclear which happens first and which happens second. This can cause different simulators to actually yield different results. That is not something that is wanted, and of course in hardware we have to know exactly what happened. So that means, and this is very important, that a coding style is required, and what we're going to learn here is how to write Verilog with a specific coding style that will ensure that what we do will actually work. Verilog has 3 coding styles, or 3 abstraction levels. The first one, and the most basic or most low-level one, is what we call structural code. Structural code, or gate level, or a net list, or GTL, is just a list of gates and the connectivity between them, what type of nets connect the different ports or pins on these gates, and how they're connected together. It's not very readable. We just have basically a list of gates and connections. It doesn't say anything. We have to go and draw it maybe on a piece of paper and try to understand, but that's really hard to do once we have a lot of gates. The second coding style is what we call RTL, or register transfer level. That's how we write what we call synthesizable Verilog. That's what we use to write Verilog that actually describes hardware that can be turned into gates. It can be turned into a gate level netlist, but it's much more readable and a more behavioral level of description. There is a higher abstract level in Verilog, which is pure behavioral, where we can write all kinds of for loops and so forth, and different things that are very abstract and can cause things to happen just like in other programming languages, but we can't actually produce, or at least not automatically produce, hardware from them. We use this for writing test benches. A lot of times nowadays we don't actually use Verilog for writing test benches, but rather other higher level languages such as System Verilog, E, or others. But the Verilog hardware language, which was actually written to write, for the purpose of writing simulations, has this support for higher level constructs or behavioral code that we'll see how to write test benches with it. Inside that, I basically pointed out this RTL and structural code are used for describing what we call the DUT, the device under test. That's the actual hardware we're trying to describe. So these things, we can actually go and make gates and transistors and so forth that will implement them. So they have to be written in this RTL or this GTL level. On the other hand, the test bench, it represents the system, and then we can write it in a purely behavioral code or a mixture between behavioral and RTL and structural, but it's very in a behavioral, and often we use other higher level languages such as E or System Verilog. So now that we have a basic overview of what a hardware description language is and what Verilog is and how the abstractions go, we'll dive down into the Verilog syntax. And we start with the basic thing, which you'll probably never use, which is a primitive. So Verilog, in the end, it describes Boolean logic gates, or it should turn into Boolean logic gates. So we have primitives for these Boolean functions, nots, ands, ors, etc. Here's a full list of what we have. And to write one of these things, like take this OR gate over here, which has the inputs in1 and in2 and the output out, we would write the word OR with parenthesis, and then we would write in order the output, comma, in1, comma, in2, and a semicolon to end it. That is not a wonderful way to describe an OR gate, because as you see, we have to order these inputs, and it's kind of like a very structural description, which is hard to read. So we won't use this much, but those are the basic types of low-level primitives that we have inside Verilog. The other thing is, well, you see we have this in1 and in2 and out, they're signals. So the signals, since they're logic signals, they can have 4 primary states. There are more things in Verilog, but they're not synthesizable, and we don't usually use them. So the 4 states that we discuss are 0, logic 0, usually like a ground voltage, 1, which is a logic 1, a VDD voltage, X, which is something where we don't know if it's a 0 or 1, and I put the X here red, and a lot of simulators will make them in some sort of a emphasized way, because this is something that either hasn't been initialized or it is some sort of an error. And we have a Z, or a high Z, which means that we have a high impedance state and we can drive something else onto the signal. So those are the 4 states we'll use, primarily 0 and 1. X is usually a mistake, and Z we have when we have tri-state things, but it doesn't appear as much. Wires are these types of nets, and Verilog, for some reason, has this differentiation between wires and registers, and it doesn't really matter why. In fact, in System Verilog, they've kind of fixed this and changed this whole concept, but in general, we have this thing called wires and regs, and I will explain later on how we get our code to compile and what the difference between them is. But just in general, wires do not keep state and registers do keep state, and we'll explain the exact little fine details about that later. Wires and registers can represent buses or groups of signals, so often we don't want to take a 32-bit bus and write 32 separate signals, wire 1, wire 2, wire 3, etc. So we bus them together with this square bracket notation. So if I want to just write a single bit, I'll write wire in 1, comma, in 2, etc., semicolon. That's how I declare a wire. For a reg, which again I'll explain the difference later, I write reg and out. That's a 1-bit reg. Then again, when I want a bus of wires, I'll write wire. Then in the square bracket notation, I'll write the MSB colon LSB and then the name of the bus. So now I'll have data 0, data 1, data 2, and so forth. And since we start with MSB down to LSB, this can also be translated into like an 8-bit number. Can do the same thing with reg. In fact, we can also make wires and regs be 2-dimensional. It's with this strange notation where we start with the square brackets before the name of the signal, then the square brackets after the name of the signal. And as you can see, reg 31 to 0, mem 0 to 7, these are 32-bit words, and there are 8 of them. So that is a way that I would basically say that I have a memory array which has 32-bit words, and they're altogether 8 words. Okay, so that's the way to do it in Verilog. In System Verilog, we can do multi-dimensional arrays with more dimensions than that. In Verilog, there are extensions for packed and unpacked data types, but I won't go into that here. So the basic constructs basically that we do use more often in Verilog than the primitives that I showed on the previous slide are the operators. And we have different types of operators. So we have and or, and then bitwise and bitwise or, and we have this type of a not. We also have a bang or an exclamation point, which is also a not, and different things like that. So what we'll usually write is, if we want to describe this type of an OR gate, we'll use one of these, either or, which is a vector-wise or a bitwise or. We'll write something like this: out equals in 1 or in 2, and that makes the same description as the or primitive that we saw on the previous slide. And that's a bit more readable, and we'll see we'll have to add an assign keyword to before that. But this is usually how we will show Boolean functionality. Constants. So constants have a strange format in Verilog. It's width and then a apostrophe, and then the type of encoding, and then the value. So for example, that kind of was strange. To say 0, just a bit of 0, we do 1 because it's a 1-bit number. This apostrophe. B means we're going to be binary, and then 0. So 1 apostrophe B 0 is a single bit binary 0. Okay, so if we want a bus or a longer constant, we have, for example, a 4-bit binary. We do 4 apostrophe B 0011, and that will give us the binary 11, or if it's in decimal, that would be 3. Okay, often if we are using binary encoding, we get these very long words, so we want to use hexa. Hexa, we just take every 4 bits of binary and turn it into 1 hexa. So we can write 8 because this is going to be 8 bits. So this number is how many bits we have in the vector. 8 apostrophe H for hexa. FF is 1111, and then another 1111. So it's an 8-bit hexadecimal, and that in decimal comes out 255. Often we like to work in decimal because that's how we think. So we can also just write D here, 255, and it will of course translate all these things into binary, 8-bit binary word. But we can use those types of encodings. Okay, next we'll discuss the heart of Verilog, which is the procedural blocks. So actually we'll start with the initial block, which is the behavioral high level of Verilog. And as I said before, the behavioral high-level abstract is non-synthesizable, and it's not how we describe our hardware, but actually how we describe our tests. So an initial block means that we're going to do something at the beginning of our simulation, at the initial point. So anything that comes inside an initial block starts at t equals 0. So it's executed only once at the first time the time unit is called. For example, initial begin, a equals 0, b equals 0, and we put several commands between a begin and an end, and this will set our a and b to 0 at the beginning of the simulation. But that obviously we cannot do in hardware. We have to put some sort of a structural thing to actually make that happen, and that will do with what we call an always block. Okay, there are also always in behavioral, and we'll see it later when we see a test bench example. So with always blocks, statements are evaluated when a change in the sensitivity list occurs. So as I mentioned before, there is something called a sensitivity list, which is which signals actually cause whatever is inside a block of code to be evaluated. So an always block, and then the sensitivity list comes after it. Anything that's inside the sensitivity list will cause the simulator to look inside that always block and do whatever code is inside. So for example, and this is a classic example, and we'll see many of them, and I'm showing you kind of classic examples so you'll get used to them. We have always, this is at, so at after it comes a sensitivity list, and inside the sensitivity list we have this word pause edge, which is a keyword in Verilog, and clock, that's the name of the signal. So every time we get a positive edge, a rising edge of a signal called clock, so we have a signal that happens to be called clock. That is a word, clock. It's not a saved word. And this is a positive edge. So every time we reach this singular point where the edge rises, we'll go in and do whatever code this is. So what the code says, if not, the exclamation point is a not, and reset, Q gets 0. So that is a reset. It's a negative level reset. So if it goes into this block, it checks what the reset signal state is. If the reset is low, because not n reset means if n reset equals 0, then this evaluates to 1 and we go into here. Then Q, the output, gets 0. It resets the flop. Else, Q gets D. And that actually turns directly into a flip-flop. Where? Okay, the flip-flop, this pin is called clock. Here we have a negative pin called n reset. Okay, and here we have a data pin, and here we have an output pin. So this directly turns into this. And that is basically an asynchronous reset flip-flop. Why is it asynchronous? Because, that's a synchronous reset clock. Why is it synchronous? Because we only evaluate this code on the pos edge of the clock. If reset, for example, goes down over here, let's say that's n reset, it will only be evaluated at the rising edge of the clock. The output Q will stay whatever it was. Let's say it was high, and then it will go down only at the pos edge of the clock. So that's a synchronous reset. We also have what's called an asynchronous reset, which we show this way: always at either pos edge clock or neg edge reset. So either when the clock rises or the n reset signal goes down, then we go in here. When we go in, we have the same code. So if we go in and reset is low, then we have a 0. Else, this is also load enabled, we have another signal called load enable. If load enable is high, then Q equals D. If load enable is not high, then Q stays the same. So what we get here is another flip-flop with, we have clock here. We have our negative edge reset. And we have an enable. It's called load enable. And we have our D and we have our Q. Okay, in this case, because we had both pos edge clock and neg edge reset in the sensitivity list, at this point when reset went down, already our Q would have gone down. Now, at the rising edge of the clock, we go into this block again. But when we go into the block, we ask what is the state of reset, and we see it's low. So Q stays low. So as long as n reset will be low, the output will stay low. Okay, so those are our procedural blocks, and there are two types of always blocks, and this is really the heart of writing any RTL. Okay, so the two types of always blocks are first the sequential block, and that's what we saw on the previous slide. So a sequential block is used mainly for describing flip-flops. So as we saw before, this code over here is a rising edge flip-flop with a low reset signal that has a load enable also on it. Okay, and how do we find out or differentiate between a sequential always block and the next type, which is a combinational one, which we'll see in a second, when there is a clock signal in the sensitivity list? So we have pos edge clock, there's a rising edge clock in the sensitivity list, and that means that this is a sequential always block. Okay, these always translate into flip-flops or latches. We're going to almost always want to describe flip-flops. Latches are a special type of a design style, and usually you're going to want to stay away from them unless you really know what you're doing and you have good reason to use a latch. So I'm not going to discuss much about latches in this course. The second type of always block is the combinational block. The combinational block describes the logic. It's purely combinational. There are no clocks that actually are in the sensitivity list causing anything synchronous to happen inside. It's just a kind of a programming language or high level or human kind of reading type of way to describe combinational logic, to describe Boolean functionality. So what we can see here is always at A or B or C. So if A, B, or C change from 0 to 1 or from 1 to 0, then we go and evaluate what's in here, and we get out equals A and B and C. So this basically just tells us that we have a 3-input AND gate with A, B, and C at the inputs. Of course, it would probably be easier to show that with an assign statement, which we'll see in a moment, but this is one way to describe just a combinational AND gate. Okay, there are no clock signals as you see here. Okay, another thing is it's very, very important that everything that happens on the right-hand side, we call this the RHS, the right-hand side of the equals, okay, and this we call the left-hand side. Anything on the right-hand side has to appear in the sensitivity list, otherwise we have to save state. Okay, so it's very important to pay attention to it. We'll see that when we discuss design styles or gotchas a bit later. So just to make sure that we don't actually forget anything, and actually it's pretty easy to understand that anything over here should appear over here in the sensitivity list. In Verilog 2001, they made an update to the standard in 2001 that you can use this operator called a star. So a star goes and looks at everything on the right-hand side and sticks it automatically into the sensitivity list. So what we write is always at star, out equals A and B and C, and then if we add another signal or remove a signal, we don't have to update the sensitivity list, which was a common cause for bugs in Verilog code before that. So our recommendation is always to use this always at star notation. Our next bullet is about assignments. So assignment is something that basically shows combinational logic. So we just saw a second ago how to do combinational logic with an always block, but that's not the only way to do it. We can do it in a few ways. So one of them is what we call an assign statement. So if we would just want to make a simple or a pretty simple type of an expression, something that describes basically a structural, some sort of an OR gate or AND gate or something that we know about pretty well, what we'll do is we'll use an assign statement often. So for example, we can describe a mux in this way. Assign, then this is the name of the output of the signal, the mux out, equals, and we have something here, so this or this. What's inside here? We have a signal called cell and a signal called in1, or not signal called cell and in1 and in1 and in 0. So what we get is mux out equals, right, we have cell times in1 or plus cell not times in 0. Okay, that is exactly a multiplexer, right? That has cell over here. For the 0, it gets in 0, and for the 1, it gets in 1. We can describe that with this ternary operator, which is kind of a nicer way to write the same thing. So assign mux out. If cell equals 1, then we output in 1, else we output in 0. So this is equivalent to writing if cell, then mux out equals in 1, else mux out equals in 0. That's equivalent to writing that. It's just kind of a short and nice notation. Okay. Our second type of a procedural block is, I'm just erasing that because it's in the way of my slide here, is we have a blocking procedural assignment, or an equals. Okay, and we saw that we used equals inside assigns on the previous slide, but we didn't describe it. So in an equals assignment, we're actually going back to kind of a sequential type of a programming language, a standard programming language, or what we call blocking, because whatever equals is here, it blocks whatever happens after it. So the right-hand side is executed, and assignment is completed before the next statement is executed. So I have a comment here. Assume that initially A equals 1. Okay, And then inside my assignment, we have a statement that says A equals 2. Now this is blocking. So now A equals 2, and then B equals A. So at the end of our code here, A equals 2, what was written here, and B equals 2 because it was blocking. Okay, it happened before this because it came before it inside our code. Then again, there's something that we call a non-blocking procedural assignment, or a left pointing arrow equals. Okay, so a non-blocking assignment, we actually do the right-hand side at the end of the current time step. A time step is a singular type of a feature inside our simulator, but at the end of the current time step, so it's an epsilon amount of time after the beginning of the time step, we do the assignment. So what happens is we take the same exact code, right? Initially A equals 1, and then we have this this non-blocking assignment. And what it happens is A gets 2. When does it get 2? Only at the end of the current time step. B gets A. When does that happen? Only at the end of the current time step. But A is what it was at the beginning of the current time step. At the beginning of the current time step, it was 1. So at the end of the current time step, when A is updated and B is updated, A is updated to 2, but B is updated to what A was initially, which is 1. So A equals 2, B equals 1. So you see we have pretty much the same code, but the output is very different. And this is very confusing, and it can cause you to make mistakes. But we have 4 rules that will tell you exactly how not to ever make a mistake with this to ensure that all simulators and everything happens exactly as you wanted it to. So what you do is you have to follow these 4 rules. First of all, in a combinational always block, so that's always at star, right? You will always use a blocking assignment, the equals. In a sequential always block, you will always use a non-blocking assignment. Just to understand the logic behind that, okay, the equals is showing a combinational type of a tree. So we have an AND gate. We may have something like an AND gate followed by an OR gate followed by an XOR gate or something like that. So this is happening before this is happening before this. Okay. On the other hand, inside our sequential block, we have a flip-flop, right? That when the clock rises, whatever was here goes over here. In the meantime, maybe stuff changes over here and it changes what was at the input, but we sampled what was at the input at the beginning of the cycle. So that's what the non-blocking assignment does. So if we keep those 2 rules, we'll always use an equals or a blocking assignment in a combinatorial block, in a combinational block, and always use a non-blocking assignment in a sequential block, where we'll be fine. Okay? Another thing is, it comes out of that is do not mix blocking and non-blocking assignments in the same always block. And something very, very important, never assign the same variable for more than one always block. What would be assigning more than one variable? Say we had one always block that described some AND gate, right? But the output was AND out. And then some other one said it was AND out. So basically these 2 are shorted together. And we can't do that. Okay? So that's a no-no. Never do this. So you only can assign to the same variable from one always block. You can use the same variable many times on the right-hand side, but it should only appear on the left-hand side in one always block. Okay, now I'll discuss how we write a module in Verilog and how we instantiate hierarchy. So a module is used to define a hardware block. So how do we make a full MUX, for example? So we have this MUX4, okay? And the MUX4, it has 4 inputs, a bus of 4 inputs, and it has a selector of 2 outputs. So this is a MUX, right? It has 1, 2, 3, 4 inputs, 0, 0, 0, 1, 1, 0, 1, 1, and it has an output, and these are called in 0, in 1, in 2, and in 3, right? And it has an output called out, and it has a selector called cell 1, 2, 0, right? Okay, so that's what we did here, and we see that we use this output as a reg. and we'll discuss why later. So we do always at star because this is purely combinational. There's no clock in here. And then we use the case statement, similar to a case in C, and we ask, what happens with cell? Now, cell is on the right-hand side, and so it goes into the sensitivity list because it's always at star. So when cell changes, when we change the selector here, okay, what happens? If it is equal to 0, 0, then out gets in 0. That describes that. If it's equal to 0, 1, out gets 1, etc., etc., etc. If we reach all of those and we haven't selected any of them, then we write a default, and default we output X's. So that's just a fall through state. If we accidentally fall through all of these, it means we say somebody accidentally deleted this line, then we output X's at the end, so it will appear in our simulator. Okay, so that's how we write a full module. We end it with end module. Now we have described this mux. There is this mux in the world. It's some sort of a component that exists, and we'll also put it in its own file, usually called mux4.v. Okay, that's our module of a mux. Now, what we're going to do with it, we're going to use this mux often and all over the place. Okay, so just as an example, by the way, that's called the header, and this is called the body of the module. So we're going to use this mux all over the place. So we're going to do it. What we're going to do is we're going to instantiate it. So in another module somewhere else, we reference the blocks or instantiate it. So there were module blah blah blah, and then we write mux4. That's the name of this module. Okay, and we call it M0. That's a first instantiation of it. Here's mux4 and a second instantiation of it. So what we did is we actually made two muxes here. This one we call M0, this one we call M1, okay? And as you see, this one is connected to out A, this one's to out B. How do I see that? As you see here, we have this dot notation. So each and every one of the ports that was described here, in 0, in 1, in 2, in 3, out, and cell 1 and cell 0, we will write them with a dot here, okay? Dot out is the output of this, and we say that's connected to a wire that belongs to the higher level module, and that wire is called out A. Dot in, and we don't have to write all four of them, it's enough to write just the name of the bus, is hooked up to A. So these guys are hooked up to A0, A1, etc., assuming that A is a 4-bit bus, okay? And cell is connected to cell 1 to 0, assuming cell is a 2-bit bus at the higher level. This one is also connected to cell, so these two are actually shorted together, but these guys are connected to B0, B1, etc. Okay, that's what we see here. You can also do this by order, so we could write the first we could write in, which would be A, comma, then cell, then comma, then out A, and that would be okay. So we could have written mux4 M0, and then we could have written in cell out A, but the problem is if somebody would come over here and change the order that it was written in the module here, this would stop working. So, and it's also less readable, so you don't want to do that. And you'll see often that machines output this type of a style though. Last thing maybe about this type of thing is a system task. There are lots of system tasks in Verilog. There are things that tell the simulator to do all kinds of things that can help us debug and help us do things in the simulation. So system tasks start with a $sign. So $sign and whatever the name of the system task is. And just example, we have $sign display or $sign strobe. They print something out to the log file once a statement is executed. We have $monitor. Every time there's a change in one of the parameters, it will print out whatever we wrote. And since these are all print type of commands, they take a C-style printf format. So for example, we can do $display. Then we use a pair of quotation marks. Inside the quotation marks, we use this percentage type of thing, which you probably are familiar with from C. So you write @%t, value of out is %b/n, and then %t maps to $time, which returns the time of the system, and or the time of the simulation, etc. Excuse me, and percentage B returns a binary number, which is out, the signal out. Okay, so that type of a thing can help us debug and print inside our simulation, though we can also use waveform viewers, which give us a graphical user interface to look at these things. So now we'll go through a few simple examples of how to write some Verilog code. So every programming language has to start with hello world. So let's write our first Verilog module. So this is a complete Verilog program. It doesn't do anything, but we have to show it anyway. So module, and we called it main. And then there's an end module that goes with the main module. And then we have initial. So this is behavioral code. This is non-synthesizable. So it can have an initial, which means it starts at the 0 time of the simulation. We have a begin to end block. And inside we have these two system calls. One says display, it prints out hello world. And the other one says finish to tell the simulator that we've reached the end of the simulation. So that's your kind of first very do-nothing Verilog code that writes out hello world. Of course, you would never do that, but let's see some practical examples of how to write RTL. So combinational logic. We have 3 different ways, or there's probably more than that, to write a mux, but let's just show them to you as examples. So we can start with an assign statement. So in a assign statement, we declare somewhere up above a wire called out. And then as we saw before, we can use this ternary operator. We say assign, then the name of the wire, out, equals the name of the selector, which is also probably a wire. Is it a 1? If yes, then connect it to an A. If not, then connect it to a B. And again, this just makes this mux where we have a hardwired A and B signals that were declared somewhere, out, which is declared as a wire, and this selector, which is also declared somewhere above. So that's what it does. It makes this hardwired assign. It's just basically a wire that goes through. Okay. We can do it using an always block. And again, this is going to be the exact same thing. It's going to infer this same multiplexer. So here we actually describe the output as a reg. Okay. So you can kind of get the idea that assigns, they output wires. On the other hand, regs are used to output always blocks. So here we have always at, and we have in the sensitivity list A or B or cell. Of course, we could have not written that and written always at star, and it would have done the same thing, and it's a better practice to do that. Then we ask if cell equals 1, then out gets A, else out gets B. And remember, this is a combinatorial block or a combinational block, and therefore we use a blocking assignment. This is a blocking assignment. Okay, only a blocking assignment. Another thing, you have to make sure in a combinational block that every if has an else. In other words, that if we have on the left-hand side some signal, which is the out, then we better know what to do with it if we don't meet the this condition. Because if we don't meet the condition, let's say we didn't have this else, we say if cell out equals A, but what happens if not cell? Then we have to keep the same state, and that would infer a latch, and that's a big no-no, or it's not what we wanted to do probably. Okay, so that is going to make the same exact mux, just using an always block. A third way would be to use an always block, but use a case statement, which we saw before. So again, since it's an always block, we'll use a reg to describe our out signal. And this time we'll again have our always at our sensitivity list. We have a case. We didn't actually need the begin and end because it's only one instruction inside, but we say case cell. What's the status of cell? If it's 0, then out equals B. If it's 1, out equals A. And again, we use blocking assignment. So these are just 3 examples of how we can write the same code. And we kind of showed the difference between a reg and a wire, which we'll get to as a real rule of thumb in a second. Let's see some sequential logic. So we already went through similar examples before, but let's say a simple D flip-flop. So here, again, to show the output, we use a declaration of a reg. So Q is a reg, and we say always at pause edge clock, Q non-blocking gets D. So that makes a flip-flop. It gets a signal clock over here. It gets a signal D over here, gets a signal Q over here, and we have a D flip-flop. No reset, no enable, no nothing. Then we have an asynchronous reset D flip-flop. So this will have a reset signal, and it will be an asynchronous reset. So again, the output we describe as a reg, and then we say always at pause edge clock or neg edge reset underscore, and I'm purposely showing you different notation for how to show a signal that is normally high and operated at low. So before we had n reset, like a negative reset. Here we have reset underscore, which shows reset, but it's kind of like should be low. We can have reset bar, reset B. Well, there are different ways of writing that. So purposely, I'm showing you different ways of calling your signals. So pause edge clock or neg edge reset. In other words, we will go into this always block either when the clock rises or when reset goes down. We don't have to wait for clock to rise once a reset is applied. That's why it's an asynchronous reset. It's not synchronized to the clock. We push the reset button, it happens immediately. And then we say if not reset, and before we use the bang exclamation point, it's the same in this case as using this inversion operator, tilde. Okay, so if not reset, Q gets 0, else Q gets D, and what we have here again is a flip-flop that gets a clock here, but it also has this reset underscore here, which is the reset, and it has this D and this Q. Okay, so that's an asynchronous D flip-flop, asynchronous reset. And just something very important, if you want to describe a latch, what you would do is again use this reg Q, and look, you don't have a clock here, you have an enable. It could be a clock, but it's a latch clock. It's a level sensitive. There's no pause edge or neg edge keyword over here. It's always at enable. Whenever enable changes, we go into this block. And it says if enable is high, then Q equals D. But there's no else. Okay? What happens if enable is low? We have to save the state we had before. Okay? So that is exactly a latch. So here we have D and we have Q, and we have this clock here, which is a level sensitive pause edge clock or pause edge enable signal. So when enable is high, D passes over to Q. When enable is low, we keep what was ever sampled before at Q. So that infers a latch. And you'll see if we do not have this else and we don't account for every possible action that happened on enable, then Q will have to be latched. And that's something we often don't want to do. It happens by mistake. Our next thing is just a short discussion of arithmetic. There have been many books and papers written about arithmetic in hardware description languages, but it's kind of easy in Verilog 2001 until you start getting into the tricks. So it supports basic arithmetic operators like a plus, minus, to add, to subtract, and you can do it on multiple bit vectors. You can do multiplication, you can do a shift left or a shift right, and there are other types of operators such as that. Division, not so fast. Division is more complicated when you want to do it in hardware, so don't just write a division operator. Okay, you can do this concatenation. If I want to connect two buses together, two wires together of multiple bits, I use this curly braces and then a comma between them. So for example, if I have a sign A equals 1100, a sign B equals 1011, when I want to concatenate them together, I use this concatenation operator, curly braces and comma A, B, and C will get 1100, 1010. So that's something that's done quite often. Okay. By default, Verilog treats all vectors as unsigned binary numbers. Okay. They're unsigned binary numbers. Okay. To make them signed, to turn them into 2's complement signed numbers, what we have to do is declare them with the word signed. So we do wire signed, the vector width, A and B. Wire signed, the vector width. Result, we can already instantiate it with the multiplication of A and B and keep it all signed. Okay. If we want a signed constant, we have to add this S before the type of encoding we're doing afterwards. So 10 SH37C will have a signed number 37C. Now, the big question of reg versus wire. And I say, oh no, don't go there, because this is the worst thing that they actually ever did in this Verilog language. And they had some great idea which kind of went wrong. So a reg is not necessarily an actual register. As you saw, we often have just a regular wire that is in a combinatorial type of an expression be called a reg. It's a driving signal, whatever that is supposed to be. It's very ridiculous, and if you do the wrong declaration, then the compiler will complain, but basically it won't be a bug. But just so we don't have these complaints from the compiler, which we will scratch our head on what we should do to fix it, just follow these pretty easy rules. So inside always blocks, either sequential or combinational, just as long as there's an always block, the left-hand side is only a reg. So here, we have an always at star. R is A and B. R is on the left-hand side. That means R is a reg. Okay? On the other hand, for an assigned statement, the left-hand side is only a wire. Okay? So we have assigned W equals A and B. Does exactly the same thing as this does. But since we use an assigned, the left-hand side should be a wire. Okay? An initial block in a test bench, on the left-hand side, it's always a reg. This is a driving signal, I guess. Okay, so initial begin, R gets 0. A delay of 1 time unit, R gets 1. R has to be declared as a reg. Okay, the output of an instantiated module can only connect to a wire. So you can never connect the output of an instantiation to a reg. Okay, so we have this module called M1, and it has some sort of output called out. Okay, and then we have in a different module, we are instantiated. So we say M1, here's an instance of M1 dot out, and we connect it to R. If we declared R as a reg, we're going to get an error. So never do that. We'd have to, right here, wire, and everything would be okay. All right, and last but not least, the inputs of a module cannot be a reg. Okay, so I have module M2 and it has an input. We declared it as input in. We cannot write reg in. We can write wire. Wire is implicit, so we don't need to write wire. We just write input in. Okay. Now, how about a test bench? We need to make a test bench to check our RTL code, which basically you surprisingly know how to write already after these few minutes of lecture. But we need to make a test bench. So the basic thing we need in a test bench of any sequential system is a clock. So how do we do that? So we have something here called a macro that I'm showing you for the first time. So this back apostrophe define clock period 10. What happens is when the compiler goes through the code, it will look for the word clock, the string clock period, and it finds it here. It will erase it and replace it with 10. That's a macro that replaces some of the text inside the file. It's very common to use this. You can use either these macros or you can use parameters, which they have different reasons for using them, but basically in the end they do the same thing. Okay, then we have initial, because our test bench will start at the beginning of the simulation run, and our clock should be initialized, so we write clock equals 0. Clock had to obviously be defined as a reg somewhere. Had to be reg clock over here, or else it wasn't gonna work. Okay, and then we write always without any sensitivity list. This is just gonna happen over and over and over again. This thing is a delay. Okay, it's a delay. So we delay by whatever comes after it. Whatever comes after it is 10 divided by 2. So we delay by 5 time steps, and then clock gets not clock. So every 5 time steps, we start with clock equals 0. That's 5 time steps. Then clock goes up to 1. 5 time steps, clock goes down to 0. So we got a clock with a period of 10, or a frequency of 1 over 10. So that's going to be how we make a clock in a test bench. So surprise, something really cool just happened. You guys know Verilog. You can actually write a state machine. You can write most of what you need to do when you're writing RTL. Let's see an example of how we can do this. We can draw a state machine, and we have a one-to-one mapping of the state machine to Verilog code. Very simple. If you can do that, well, you've just become a digital designer. So let's start a state machine example, and it'll be a 4-bit counter. Our 4-bit counter has 4 inputs. It has the system clock called clock. It has a low reset. This time we call it reset_n. It has an activate signal, which is kind of an enable. It says if we're going to count or just do nothing. And it has another signal that says if we're going to count up or down. So if up is up, if this up down n is 1, then we're going to count up. If it's 0, we're going to count down. Okay, it has 2 output signals. One of them is count. It's a bus that tells what the value of the current count is. And one of them is overflow. It says if we passed 1, 1, 1, 1, 1, or we went below 0, 0, 0, 0, we overflew. So just taking that as our interface, we will define our header. So we call the module SM for state machine. Okay, and we have our port list: clock, reset, n, act, up, down, count, and overflow. We also added this other thing. Look, this is not a delay. It's a parameter declaration. Okay? What we're going to do here is we're going to declare a parameter called counter width, and we're going to say its default value is 4. So this is the default value. However, we can see afterwards in our test bench, when we instantiate this module, we can override this default value. But right now, we're going to write our code as parameterizable as possible, so we can make this work for different counter sizes. By default, we'll start with a 4-bit counter. Okay, then we have all of our inputs: clock, reset, act, up, down, n, and I put them on separate lines. I could have separated each 1-bit signal with a comma, but it's better to put them on separate lines because then we can kind of see them. We can add some sort of a comment here like system clock or something like that, and that gives us a better and more readable code. Okay, then we have our output. Our output is this count, and the count is parameterizable, the size of it. So if it's 4 bits, that means we have to have it 3 to 0. So that's counter width minus 1 to 0. That is equal to 3 to 0 in this case. But as I said, we can override that and make it 1,000 to 0, right? And then we have our, this is a mistake here, sorry, output overflow. We have our output called overflow, and we also declare that as a reg. We could have written output reg overflow, and it would also work. And then we have, we also describe count as a reg, and we have state and next state as 4-bit vectors, and we'll see in a second why. So let's draw the state machine here. Okay, we start with one state called idle, and when we hit the reset button, we go back to our idle state. Then if we stay with our activate signal at 0, we will just stay inside our idle state and not do anything. What happens afterwards? If our activate equals 1, then we have to check. If we're counting up, if up down is 1, then we go to a state called count up. If up down is 0, we'll go to a state called count down. In this state, we will increment our counter. In this state, we will decrement our counter. Now, if act goes low on the next clock cycle, we'll go back to idle and not change anything. And then if act goes high again, we'll either count up or count down. Okay? Next, if we stay with act equals 1 and we have up down equals 1, we'll count up again. Or if we have act stays high and we have and up down stays low, we'll stay in this state. On the other hand, if up down changed, we have to cross between the states that we were at. Now, one last thing, there's an overflow condition, and if we reach the overflow condition, we'll go to a state called overflow and we'll get stuck there forevermore. Plus, our output called overflow will go high. So this is our state machine of our counter, and now we'll see how we encode this into Verilog very straightforwardly. First of all, we have these different states, and since there are 4 states, we can use just a 2-bit vector to describe all 4 states, but what we should do is we should enumerate them. We should give them names, so we don't call them 1, 2, 3, 4, but rather call them idle, count up, count down, and overflow. What we use is we use something called a local param. We could also use a parameter. We could also use a tag define, but the best practice is to use a local param. We say this word idle is actually a state. And what we decided is an encoding called one-hot. There are different ways to encode state machines. We decided on the one-hot encoding, so for each state we need a bit, and we called idle 0001, count up 0010, etc. Okay, so we'll be using these words in our code. It makes it much more readable. Next, we go into writing the combinational block. What we have is, if you remember, we declared two registers, state and next state. Both of them were 4 bits, and 4 bits because we have the 4 states that are one-hot encoded. Okay, so what we're going to do now is we're going to have completely combinational logic that will compute what the next state of our system should be once the clock rises. Okay, so how do we do that? It's combinational block, so we use always at star. And we actually don't care what's in the sensitivity list because this star will decide by itself. Then we start with a case. And we want to know what the current state is. So it's case state. And depending on the state, we'll do different things that will exactly describe our state machine. So let's start with the state idle. What do we know about idle? If act is 0, we're going to stay in idle. If act is 1, then depending on up down, we're either going to go to count up or count down. So we ask if act is 1. If not, it's easy. We're going to stay at 0. But if it was 1, then we look at the state of up down. So we say if up down is high, then we're going to do this path, and we're going to be in the count. The next state is going to be the count up state. Else the next state is the countdown state. So we have completely described all of the arrows pointing out of this idle state. Next, we can go over to the count up. It's a bit more complicated. What do we have in the count up? We have this arrow. When act goes to 0, we will idle. When act stays at 1 and up down stays at 1, we'll stay in count up. And when act stays at 1 but count down goes down, we'll go to count down. On the other hand, we have this arrow that when there is the overflow condition, we have to go into overflow. Okay, so first we have this big if else, right? That if act, then we go into this block of code. If not, we go next state into idle. That was basically this arrow. Okay. If act is high, though, we go into our code block here. Okay. So then we ask the situation of up down. If up down. So now up down is 1. That means we're going to be counting up. Here we can look at our overflow condition. When do we overflow? When we have a situation when we have, say we're a 4-bit counter. If it's 1, 1, 1, 1, and we want to go up, our next state will be an overflow. So how do we actually describe that with a parameter? It's tough because we don't know what our state. We can't say if count equals 1, 1, 1, 1, and if we had a 5-bit counter, it wouldn't be sufficient. So we play a little trick. Okay, we do this. We take 1. 1 is 0, 0, 0, 1. Okay, and there would be a whole bunch more zeros if we had a longer, if counter width was higher than 4. And then we shift it left by counter width. So we go 1, 2, 3, 4, and we get the number 1, 0, 0, 0, 0. That's 5 bits. Right? 5 bits. Okay? Guess what? If we remove 1 from there, minus 1, we get 1, 1, 1, 1. Okay? If that's what, then that's what we wanted. And that works for any bit width. So our condition over here to get to the overflow state is if count equals 1 shifted left by counter width minus 1. It's a little kind of trick that digital designers have developed over the years. Okay, so if that happens, our next state is obviously overflow. If not, then our next state stays at count up. Else, okay, if count is 0, then the next state is overflow. Else, the next state is count down. So if we were here, I don't know how we'd be here with count 0, but if we were, then we would overflow if we would go, if we were going to try and count down from 0. So that's basically our description of count up. Our description of count down is exactly the same, just we kind of changed the conditions. If you saw before, I wrote for B0, but we actually wanted a variable width. We could have written counter width B0, or we could just leave it empty, and Verilog will use this as an extendable 0. We could have also just written 0, and it would have been fine. Finally, we have our overflow state. And in our overflow state, we want to stay always in our overflow state. So in case overflow, next state will be overflow. Finally, as I told you, that we have to always put a default condition on our case statements. That's just in case for some reason there was some glitch or we made some mistake and we got to a state that we shouldn't have been at. In that case, we want to show that there's an error in our simulation. So we say, first of all, our next state is in X. Okay. And second of all, we write some sort of an error message on our log file. So that is our combinational description. But how do we actually move between the states? And it's really easy. We have a sequential block. Okay? So the sequential block is really simple, and you'll see this almost exactly like this in every state machine. Always at pause edge clock or neg edge reset. If not reset, state equals idle. That described this error here. If reset goes low, then we go into the idle state. Else, state gets next state. And you see this is a non-blocking assignment because it's in a sequential block. So every time the clock goes high, state goes to next state. We traverse between these guys. Okay? It actually made a bus of flip-flops. They're the state flip-flops. There is a signal coming in, or a bus of signals called next state. And when the clock rises, next state turns into state. And this goes back into our combinational logic that figures out what the next state is. And that is how we made our state machine. We have one more thing that is synchronous, which is this count. So every time that we're in count up, we're going to increment our counter. Every time we're in count down, we're going to decrement our counter. So always at pause edge clock or neg edge reset, we have this asynchronous reset that will put our counter back at 0. But if state equals count up, we're going to increment our counter. If state equals count down, we're going to decrement our counter. And basically, we're almost finished now. One thing is left is this overflow signal. In all these three states, I didn't draw it on the picture, overflow is 0. Only in the overflow state, overflow gets 1. That's purely combinational. It's dependent only on the state, and it doesn't depend on the clock. So in a Moore machine, we're going to output assign overflow equals, if state equals overflow, then output a 1, else output a 0. And that's it. We hardwired the condition for a 1 output on our overflow. Now we'll write a test bench for our state machine. So module state machine test bench. We give some sort of a parameter, and we call it width. And this will be the width of our counter, but it's the width at the state machine level, at the test bench level, not at the device under test level. And we decided we'll instantiate a 5-bit counter, not a 4-bit counter, which was our default for our state machine. We have regs for all of our signals that will be inputting to the our device under test, and we have wires for the outputs from the device under test. Remember, we cannot connect an instantiated block to an output reg. So we'll instantiate the machine. We write SM, that's the name of the module, not this module, the module we described above. We called it DUT, but we passed a parameter called width. So that will override the default parameter, which was 4, and it will make a 5-bit counter. DUT will be a 5-bit counter and not the default 4. And then we have the dot notation, which connects all of our signals that we just declared here to our signals, to our ports of the module. It was very convenient to just give them the same names. And that's something we'll often do, especially if there's only a single instantiation of that module inside our higher level hierarchy. Okay, now we'll start our simulation. We should initialize different values. We'll start clock high, we'll start reset low, we'll start activate low, and we'll start up, down, high. It didn't really matter how we would start these. We have to reset and release the reset. Okay, and we'll put some system tasks. We'll monitor the different signals here, and we'll have them print out on screen. And then we'll have a delay. Remember this, this is a delay, so we'll delay 100 time units, and after 100 time units, we'll release our reset by raising it to 1. We have to define a clock, so we saw that's pretty easy. We'll just do always every 5 time units, clock gets negative clock. And now we'll start our stimuli. Okay, what are our stimuli? At 100, because up till 100 we were in reset, we'll start counting up until we hit overflow. So we have a delay by 100 because the first 100, it didn't really matter what we were doing because we were under reset. Okay, at time step 100, we'll raise our activate signal, and we'll start with our up-down signal being high. That's a count up. We'll count up for a long time. For how long? 1,000 time units at a clock period of 10. That's 100 cycles. Since our counter was only 5-bit, it will very soon saturate and overflow. Okay, so what we should see in our test bench is we hit an overflow. And if you take this code and run it in a simulator, that's what you will see. After 1,000 cycles, we can reset our design. Wait 100 cycles, 100 time units. We didn't need to wait that long, but we did. And then we will release the reset. Now, our activate will have to go high, and our up down is supposed to go. So we started counting up high here, and then for four cycles we counted up high, so we got to 4, and then turned up down to low, and started counting low forever more until it actually saturated, basically 40 time units or 4 cycles later. So that's a way we basically tested almost all of our signals, or hopefully all of our signals and all of our states in our state machine. That is called a directed test. It is not a formal verification. It's not even a good type of a verification, but it's what we want to just do to test that at least our basic functionality works. As I promised, we're going to have a short break in the middle of each lecture to discuss the IEEE Chip Hall of Fame and bring different types of chips that are famous from the past. And here's a kind of a personal chip. We started with the Intel 4004, which was the original microprocessor, or Intel's first microprocessor, but Intel really broke out with the 8088 microprocessor. And here you can see a picture of it here. You can see it's a bit big. It had a bit more pins and so forth than the 4004. It's a later version of the Intel microprocessor. And the reason that it became so successful, and the reason that it's such a famous chip, is because IBM selected this chip to put it in their PC, their personal computer, which brought the computer into our homes and is the best-selling computer of all time. And it was based on this Intel 88 processor. It was released in July 1979. It had 29,000 transistors. If you remember from the last lecture, the 4004 only had 2,300 transistors, so that's already an order of magnitude higher. It ran at a 10 megahertz frequency versus a few hundred kilohertz for the 4004. It was in a 3-micron CMOS process versus a 10-micron PMOS process for the 4004. And it had a 16-bit x86 architecture, but actually it had an 8-bit output bus. So first of all, this x86 architecture may look familiar to some of you because it's the architecture that is still used today in Intel and AMD machines, and it's one of the 2 leading architectures in the world, along with the ARM architecture. And it became famous because of this IBM PC and because of this 8088 microprocessor. But it's very interesting because the better chip that they put out was the earlier 8086, and that's why it's the x86 architecture, because this is the architecture that was built for the 8086. But there was a problem that they wanted to make the IBM PC a cheap computer, and most of the other chips around worked on an 8-bit bus. So they had to take the 8086, which was 16 bits, and remove the external 8-bit outputs. So what did they do? They sent it up here to Israel, to the young Intel team in Haifa, and they asked a guy who I happen to know to castrate the 8086, and a few months later he came out with this 8088, which was not as good a chip as 8086, but it was the big success. So I know something that maybe Gordon Moore and the other Intel management doesn't know about this chip, because I know the guy who designed it. Well, do you see something strange about this chip? Let's take a zoom in on this top right corner. And I don't know how many of you know Hebrew, but I guess Intel didn't, and they weren't able to erase this. But here it says the Resh Pei Yud, which is Rafi. And that is the name of a guy named Rafi Retter, who was the designer of this chip. And Rafi told me that Intel wasn't allowing the designers to write their names on the chips, and they were erasing them. But doing it in Hebrew, the management didn't see that he wrote his name on it, and that's how it was taped out and sold to the whole world. So now that you know everything you need to know to write RTL, well, maybe not everything, but at least enough to write a simple state machine, I want to discuss a summary kind of the coding style that you need to adhere to in order to make sure that your design will actually work. So, as I said, an HDL is not just any other programming language. At least it shouldn't be. You have to treat it right, okay? Verilog is very rich. It has commands and constructs that can let you do many things, and you can buy books that show every single type of thing you can do and every difference between Verilog 2001 and Verilog 95 and so forth. It was originally designed as a verification language. There's a lot of things you can do. But when you're designing hardware, you're designing these DUTs, you can't actually do whatever you want. It's very important to file these rules and coding styles to make synthesizable code. Okay, in the following slides, I'll introduce you to a few guidelines and rules, and we will revisit this later after learning about synthesis to learn some other things that you can get to know. Also, you have to have some hands-on experience to understand some of the things we'll be discussing. So let's just discuss some basic rules of how I recommend organizing your code. Okay, so each module should be in a separate file. You should name the file module.feed. That makes it really easy to find different modules, to take them between different, to move them between different projects, etc. So write each module in a different file. You don't have to be cheap and have only a few files or put a lot of things in one file. Okay? Always, always, always connect your modules with a dot form. And that's just in case, I mean, it makes it much more readable, and in case somebody changes the order of the inputs and outputs in the module header, it won't ruin your code. Write each input and output on a separate line. And the reason to do that is that it makes it a bit more readable, and you can comment what each signal is used for, as I showed before. Separate sequential and combinational logic. There are different coding styles. Some people like to make these big sequential blocks that have a lot of stuff going on. From my experience, each and every flip-flop is very important. You want to have personal knowledge of every flip-flop. You want to check that it was how it was synthesized, what came out, and so forth. You want to be friends with the flip-flops. Give them their own always block. Have always at pause edge clock or neg edge reset for an asynchronous reset, and have your sequential code, which should basically be state equals next state. Then all your combinational stuff, put it in its own block. Or assigns, you can have simple things. You can write a lot of stuff in assigns. But just separate, don't put all kinds of cases and so forth inside your sequential blocks. It really makes a mess. It makes it hard to read. It makes it hard to recognize your flip-flops, and it's room for bugs. Assignment. So just to make sure you got the rules that I mentioned before, in a combinational always block, so the always at star type of stuff, you always use a blocking assignment, this equals. Okay? We highly recommend you to use this star. It will cause you not to have all kinds of stupid bugs in your code. And always use full case statements. If you don't have a full case statement, such as using one hot encoding or something like that, use default to propagate x's. Always use default to propagate x's and show in case there was a mistake, some case that you reached that you didn't want to. In a sequential, always at pause edge or whatever block, always use a non-blocking assignment, this smaller than and then equals. Okay, prefer to have each flip-flop in a separate always block. Really give these flip-flops their their right due respect. and prefer data enabling on all sampling. So if you can, it will help you save power. Never, 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 never assign a left-hand side for more than one always block. That will cause a contention, a short. It's a mistake. Okay, be really careful not to infer latches. This usually happens to rookie HDL designers until they get used to it. Okay, if an output is not explicitly assigned by every signal in the sensitivity list, a latch will be inferred to save the previous state of the signal. Okay, for example, what happens if cell equals 1, 1? We don't have cell equals 1, 1 here, right? We have to have a latch to save the state. The same will happen if an output is not assigned in all branches of an if-else block. An if must have an else, or it's actually for every left-hand side assignment, we must have both an if and an else to make sure that it's assigned from every single state of that if statement. If not, we need a latch to save the previous state, and we probably didn't want that latch there. And stay away from tri-states. Don't assign a z. Digital designers don't like it. In some places you will use them, but that's in very specific places where you really know what you're doing and your company decided that that's what you have to do. Okay, stick with one reset type. The purpose of reset is to bring your design into a well-known state, such as in our state machine, it was to bring it into that idle state and to bring the counter to 0 at the beginning. It is desirable to have every flip-flop resettable, whether or not required. It costs a little bit more in area, but really it's worth it. Again, it keeps us away from weird bugs that are really hard to find and so forth. So just make all your flip-flops resettable. Okay. We usually use asynchronous reset, always at pause edge clock or neg edge reset, but there are a lot of people who like synchronous reset, and that's also fine. Just make sure you don't mix and match them. There are a lot of arguments between the async and the synchronous reset guys. You can read one. I think I put one of the papers about it on the references below. Okay, another important thing that I've seen a lot of rookies make a mistake: do not put logic on your reset signal. Assign something equals a and reset, or always at blah blah blah, you have reset on the right hand side. No, reset, like clock, is a very special signal. It should have no logic running on it. Nothing should be done to it unless, again, our architect tells us we need to do some sort of special clock gating or reset gating or something like that. But these are very specific things that we know about very well, and they're in the architecture of our whole system. Parameterize your design. Pretty code is code that is completely parameterized. There are two options. We can use compiler directives, macros. There's defines, includes, if-defs. They're really nice to make our code take care of a lot of different cases. Okay, you can put all the defined statements in an external define file and just use an include, and then make it adaptable to different technologies and so forth, different projects. Okay, parameters or local params. So parameters, we saw that we can pass a parameter to an instance, so they're really nice to use when we need to override something like the counter width we saw before. Local params are better for enumerating type of constants such as the encoding in FSMs. So we don't ever want to have somebody override them, so we should use a local param and not a parameter. There's something called a generate statement in Verilog, which helps you make code that can produce a lot of things. It's a bit complicated. It's out of the scope of what I want to teach you today, but you can read about how to use them, and you may need to use them in the future. Always encode the FSM state with hard-coded values. You have to choose between different ways: binary, gray code, one-hot, etc. There are, again, lots of philosophies on this, lots of papers about the pros and cons of each type, but encode them with hard-coded values, give them names, makes your code much more readable, and that helps us not make really bad bugs. Write readable code. That's really important. Always use indentation. Okay. And naming conventions. So this is a toughie. I don't have one winning answer, but you should always keep to a naming convention, decide what your naming convention is, and use it across your code. There are different types. There's C style, Pascal style, and modulo style if you're using these underscores to separate words, or if you're using this camel case where you have capital letters and lowercase letters that separate words. Just try to keep to one of them and not mix and match between them. It really drives you nuts if you mix and match between the two. There is no right answer. I found online 2 recommended styles. One's from NetFPGA, gave this Verilog coding guidelines. They have a kind of a nice style that I like. And there's something from ETH Zurich, the VHDL naming conventions. It's, in my opinion, a bit ugly, but it's it keeps a good order, and it lets you make all kinds of macros that can parse your code and highlight different inputs and outputs and signals that belong to each other, and even do automatic connections of things. So it's worth taking a look at, even though each and every signal gets a lot of characters that are kind of hard to read. So just some helpful documents and references. So as I said, I put a reference on wires versus regs and the whole argument about them. Something about signed arithmetic in Verilog 2001s, what to watch out for. Some Verilog coding guidelines, as I mentioned, from NetFPGA. MIT has some nice lectures on Verilog, and there's a lot of papers in the Synopsys users groups and the Cadence CDN Live that you can find online. Something from Stuart Sutherland and Don Mills is called Standard Gotchas. There are actually 2 versions of this. Once you get to know a bit more Verilog, you should sit there and read them. They're pretty long, but they'll tell you a lot of things to stay away from and how to do them better. So that's all I have to tell about Verilog for now, and we can continue on next week with synthesis.